Hi, so my name's Ted, but you can call me Ted. Can you guys see what I'm doing? I'm trying to start a slideshow. There we
Yes,
go.
we can see it.
Welcome to reinforcement learning with intrinsic rewards based on the free energy principle. So there are a lot of words in that title, and we'll go over it bit by bit. But the reason I'm giving this particular presentation is because I'm actually publishing a paper about this. So reinforcement learning is machine learning with neural networks and such, where robots can earn numerical rewards by pleasing us. So we can give them rewards, like if the robot does something we like, we can give it a positive reward. And if the robot does something we don't like, we can give it a negative reward. That's not a reward, that's a punishment. So we can give these robots pleasure, or we can beat them around until they do what we want. So what kind of machine learning is that? Well, if you've studied machine learning, you generally know two types. In supervised learning, neural networks are trained to output predictions. So those predictions are close to correct answers, which we provide. It's supervised. So for example, we might give it a bunch of pictures and say, these are dogs and these are cats. We're going to give you a picture. Is this a cat or a dog? There's another kind of machine learning, unsupervised learning, where we just let algorithms investigate data all on their own. So we give it data, make this data into 5 clusters. What kind of patterns are there that we as humans can't just find like that? So reinforcement learning is not quite supervised, and it's not quite unsupervised. Reinforcement learning is sometimes called self-supervised learning. When a robot gets observations, the robot chooses actions, and those actions lead to rewards and more observations. So the robots sort of get to choose what they're looking into, what they learn. So because of that, exploration is critical. Robots need to find information. They can't exploit anything until they discover it. So how do people feel about that so far? I should tell you, when I practice this presentation, it lasts about 45 minutes. So we should be done before the end of the hour. All right.
Very clear.
The free energy principle, when you read anything about it, it's going to go right over your head because you have to just keep reading stuff about it for like 2 years until you finally understand what the heck it's talking about. I still don't entirely know what it's talking about, but I've gotten it to work. So first of all, I don't like the name. The name free energy principle makes it sound like we're trying to break thermodynamics by making free energy. That is not what we're trying to do. There's a neuroscientist named Carl Friston from the UK, and he says that biological agents, like us, we are biological agents, being humans and all that, we seek to minimize free energy, which is a mathematical term in Bayesian statistics and information theory. And our goal is to minimize this. Now, another way to say this, because we're talking about energy in terms of information theory, we are trying to minimize surprise. We're trying to minimize uncertainty. And the way that you do it is by exploring the environment until we know how things work. So we'll go back to this. The free energy principle, it's very important, but I think we're going to have to cover a lot of stuff before then. So for now, let's explore a maze. It looks like we can go forward, and then maybe we can go to the left and then to the right. Is there anything behind us? What is there behind us? Okay, so it looks like there's nothing behind us. So I guess the only direction we can really go is forward. So everyone, raise your left hand or your right hand. Do you think we should go to the left or to the right? No, left hand for left, right hand for right. Well, unfortunately, as we've talked about, I can't see you right now. So, and also this is a video that I already made, so I'm afraid it's up to me. And I don't want to go left or right. I want to move forward. What happens if we go forward? Oh, it looks like we bonked against a wall. We bonked against a wall, and we didn't like it. We got a reward of -1. We don't like bouncing off of walls. So let's try going to the left. Oh, well, this was an incredibly easy maze, wasn't it? There's an exit right there. Let's leave. We found an exit to the maze, and we got a positive reward. So I think we understand this maze pretty well. So let's just do that again. We can move forward, we can turn to the left, and we can get that reward. Oh, we're experts at this maze, aren't we? Let's just keep doing that. We know how to get rewards. I mean, heck, we can just keep doing it. But I think I know what you're thinking. We've never looked at the right. But why would we? Why would we look to the right? We already know we can get a reward right there. Well, I don't know about you. I'm pretty sure as a university students, you're pretty curious. And I'm kind of curious too. Let's take a look to the right. Well, it looks like there's a hallway. There's an obstacle along the way. Maybe we should just turn around. I don't see a way to get a reward over there. We already know how to get a reward, but you know what? I think satisfying our curiosity, that is a source of reward. We can reward ourselves. So let's see what's around this hallway. Oh, there's another exit. We were missing this exit the entire time. And now we got a much bigger reward. That's a reward of 10. It's worth 10 times the other exit. So let's zoom out. Let's fly away like we're some sort of incredible deity. So I made this maze in a physical simulator, a physics simulator called PyBullet. It's based on Bullet, another physics simulator, but it's made specifically for Python. We were a duck, by the way. There are a lot of resources in PyBullet, but somehow they don't have a mouse. They don't have a rat. So we were a duck. So we're this duck over here, and I want to make a robot do this for us. Ignore the question marks. We're going to come back to the question marks eventually. But you'll notice on the left side, going forward and then left, there's a bad exit. I haven't marked with an X because I'm calling it the bad exit, the wrong exit. You can get a much better reward if you come way over here. That's the good exit. It's a check mark for good. I mean, this one, we got a reward of 10 compared to a reward of 1. So it's probably better to take this exit over here. But we are going to make this a little bit more complicated for this duck. Here's how this will work. Well, first of all, this duck gets an observation. It can see pictures just like we were seeing pictures. The pictures are 8 by 8 by 4. You already know the channels are red, green, and blue, but now we have a fourth channel. It's distance. So it's as if the duck has a depth perception. And the duck gets to observe its own speed. It knows how fast it's moving. So here's an example. This is what the duck is seeing. The duck gets to see that it's at speed 0. It's not moving. And look over here. This is the view from the perspective of the duck. It can see this sort of brownish red block on its left, this cyan one and this purple one, this gray one and this sort of olive green one. And over here, this second image, that's actually the fourth channel distance. So this block over here, it's quite close. So the distance is well, it's a very light colored object. These blocks are farther away. These are even farther away. And it looks like there's just sort of empty space all the way around. So this is what the duck gets as an observation. And it's supposed to use this observation to choose its velocity, its speed, and its angle. You'll notice when we explored, we were exploring in a very discrete manner. We were only making one of 3 actions. We were turning left or right, or we were moving forward. So that's pretty easy. There are only 3 possible actions at any time. But when you're choosing a velocity, the speed and the angle can be any non-integer, any floating point number. So we call this continuous action space, where there are so many actions, an infinite number of possible actions. If the duck doesn't find an exit, doesn't choose an exit within 30 steps, 30 times choosing its velocity, it will actually be punished with a reward of -1. So it's got to find an exit. If it collides with a wall, we're punished with a reward of -1, just like we were. If it chooses the better exit, remember this check mark is the better exit, we got a reward of 10. But actually, when you choose that exit, you flip a coin. Maybe you get a reward of 10, but we were lucky. There's a 50% chance you actually only get a reward of 0. It's still the best exit, but it's more difficult to determine that, because you might go all the way over here and get a reward of 0 and say, well, that was a waste of time, and keep going to the exit on the left. And finally, positive rewards are reduced based on how much time it took to acquire them. So if the duck gets a reward at either of these exits, the reward is actually scaled down. It's multiplied by 0.99 to the power of how many steps it took to get there. But that's the entire deal here. How can we make a robot do this for us? How can we make a robo-duck? Please feel free to interrupt. I can't actually see people right now, so we'll get through this. So reinforcement learning. This is how we can make a duck do what we want. And specifically, I'm talking about the actor-critic method. There are a lot of different ways to implement reinforcement learning. Reinforcement learning is very broad. There are a lot of different ways to do it. I like the actor-critic method because it's pretty standard, and it's one of the few ways to do continuous action spaces. There are a lot of different ways to do discrete action spaces because you can just think about using every possible action. When you have a continuous action space, that's not really an option. So how do we do an actor-critic method? Well, first of all, in every episode, every time we start the maze and until the maze ends, we can call that one episode. And within that episode, there are steps at time value t. So every step contains an observation, OT, an action, AT, a reward, RT, and a next observation, OT plus 1. There's also a Boolean value, Boolean, so it's either true or false, 1 or 0. We call it done, which is 0, false, if there is more episode to continue, or 1 if the episode is over. Maybe the duck chose an exit, or maybe the duck ran out of time, so we can decide if we're done. And every step, we're going to have an actor. This actor is a neural network, which we call pi. And we call it pi, I believe, because another way to say actor is policy. Policy, meaning in this situation, this is what we do. So the neural network, pi, has, oh, this is embarrassing. Is this a fee? I believe that's a fee. Someone correct me if I'm wrong.
Yeah, it is.
Okay, so this neural network, the phi represents all of its parameters. So the pi represents the architecture of the neural network, and the phi represents all of the parameters in that architecture. This is given an observation as an input, and it outputs an action. And it's trying to choose actions which maximize a critic's predicted value. So this critic, it's a neural network, which we call a Q. Sometimes we call it a Q network, because the value we're trying to predict is called the Q value. And here we have theta, which also obviously has all of the parameters for this neural network. So this critic gets an observation and an action chosen probably by this policy, which it uses to predict a value. And specifically, the value that it is trying to predict looks like this. This is the Q value. It is equal to the reward. So when the actor performs an action, it gets this reward. But then, if there is more episode to go, if the episode isn't over, we're going to include expected future value. meaning that we're not just thinking about the reward now, we're also thinking about future rewards. And this value here, gamma, is how we say how much we care about the future. So this equation is called Bellman's equation, and I think you might have noticed that during the video of us walking around the maze, we only got rewards or negative rewards sometimes, meaning most of the time we were getting a reward of 0. Rewards can be pretty sparse, and sparse rewards are another reason that you need to include Bellman's equation so you can think about the future. And also, it's a reason that we need more exploration, because if rewards are sparse, we need to look for them. Are there any questions on this side before I make it more complicated? All right, sounds like we're good. We're using recurrent neural networks. So recurrent neural networks are used when one observation, it actually depends on a whole sequence of things. So if we have, for example, text, if you're using ChatGPT, it's using a recurrent neural network, meaning that it's not just seeing one word at a time, it's also considering all of the words that it has seen up to that point. So recursion depends on hidden states. H means hidden states. And so we have a hidden state 1, which is generated using this recurrent neural network, using the observation and the previous action. So these bars represent concatenation. You're combining the observation and the action so that we can make something which represents everything that the duck has understood so far within this episode. And every time the duck chooses an action, it updates the hidden state so that the duck always has something it can look at to say, this is everything that I know so far within this episode. So in addition to having an input, which is the hidden state, it also outputs hidden states to use in the future. Here's a little visualization of that. We get an input, but in addition to the input, we get a hidden state, which is this H. And then using the input and a new hidden state that we're generating, we produce an output. But then this hidden state, it's also looped back around because we're going to continue using updated hidden states. I think it might be a little clearer to unfold it. Unfolding a recurrent neural network means that instead of just having one thing that has the hidden state circling back to itself, we can have different steps sort of represented like this, where we're getting one input, we make a hidden state, we make an output. This new hidden state is passed forward so that when we have a new input, we can also consider the previous input. So, for example, the actor could have this, where in addition to an observation, it's also seeing the previous action and the previous hidden state, and it makes a new action and a new hidden state. And the critic can have an observation and an action and a previous hidden state, and make a prediction and a new hidden state. So I think this is really complicated, and it took me a long time to understand how these things work. So I would be glad to have any questions here.
Hi. So I just wanted to clarify what exactly this H is. Does H sort of intuitively represent kind of the internal reasoning of the model or kind of the internal conclusions, like what it's made? Is that a good way to think about what H is?
I think that's a great way to think of it, and a great question. If we receive an observation, but we don't remember anything that has happened before, and also like a textbook full of information that someone else who has been working with these observations before has written about all previous observations. And when we pass this along, we're going to update that text. And we're going to only include information that we think is relevant. So I think it's a good way to say that it is like a worldview. It is how the agent understands everything that has happened so far, and specifically, it's only paying attention to what it thinks is important, how to accomplish a goal, and what information it needs to do that in the future.
Thank you.
All right, so what's this next slide? We're going to use 6 different kinds of ducks. I think maybe we can come back to this later if we're really interested in particular equations and particular parameters. But right now we're starting with a very basic duck. I'm going to call them N ducks because they don't have entropy and they don't have curiosity. And what are those things? Well, we'll find out later because the other ducks have lots of stuff. So regular old ducks working in the way that we've described using the actor-critic method, how are they going to do this? Well, here's an example of a duck training. Look at that guy. So he's slowly learning. Every time he loses, he starts again. But now you can see he's doing exactly what we did. He found the reward on the left exit. And so he's going to the left exit. Why would he do anything else? So if we go to the next slide, this is really cool. We have a video here, which is showing how these ducks trained based on however many epochs they have been training. So I trained these ducks for about 5 minutes. This is 36 separate ducks. And this is after not training at all. This is before training. And you can see they're sort of moving around in completely meaningless ways. But if we go after 1 minute of training, they have 1,000 epochs worth of training. A lot of these agents have found the lesser exit, the bad exit. Some of them are just sort of spinning around because they're not sure what to do with their lives. It looks like one of them might have found the better exit at this point. But if we keep going, this is 200 epochs, 300, 400, and 500. So you can see most of these ducks are going to the exit on the left. After training for 5 minutes, that's their best course of action. That's what they think is right to do. A lot of these ducks have found the better exit on the right side. And so now that's what they're doing. I'm not sure what this duck is doing. this red duck here, he's doing his own thing. I don't know. But if we look at this graph, this is how I'm sort of judging how well these ducks did. I didn't actually train 36 ducks. I actually trained 360 ducks. That's a lot of ducks. And this is how I'm gauging agents' performance. So this is a biased T maze because it's a T maze. It's a maze which is just the letter T, left or right. It's a biased T maze because the exit on the right is farther away and there's an obstacle in the way. It's a bias.
I have a question. Sorry, Ted. Philip has a question.
Oh, sorry. Go ahead.
Yes. Sorry, I thought maybe you could see that reaction.
Oh, sorry, I can't. I'm afraid.
Could you please clarify what an epoch is?
One epoch. I'm not sure about a technical description, but in layman's terms, it means that we have given an agent a batch of information, a whole lot of information, and the agent has its neural networks trained using that information. So, for example, the critic might make a prediction of a value, but now we have a more accurate value. And so we can perform back propagation so that those neural networks are more likely to get closer answers in the future.
So maybe, is it reasonable to think about it as like one sort of engineering cycle for the model?
Yeah, I think that's the perfect way to put it, an engineering cycle. So over here, there's just sort of a bar, and this is N, meaning no entropy and no curiosity. You'll notice there's a lot of empty space, and that's because we're going to look at other ducks in the future. And this is the proportion of correct exits in the last 10 episodes. So these ducks, they tried these mazes 500 times throughout training, once for each epoch. And in the last 10 episodes, in the last 10 epochs, it looks like they chose the correct exit about a quarter of the time, about 25% of the time. This bar plot here is the confidence interval, we are 99% sure the correct proportion of ducks choosing the better exit is in here somewhere. So we're pretty confident about it. And I'll say these ducks aren't doing terribly well. 25% of the time, those aren't very successful ducks. How can we make these ducks perform better? Find the correct exit more often. One way is entropy. Entropy is a term which means a lot of things in a lot of different branches of science. In reinforcement learning, it means a particular thing, which we'll see on this slide, and it's generally consistently defined. Those ducks that we just watched, all they had was extrinsic rewards. All the rewards they got were provided at our discretion. We said how much it gets for hitting a wall. We said how much it gets for going to this exit. We say how much it gets for going to the other exit. But that's not the only option. There are intrinsic rewards, which the ducks make for themselves. And that boggles me a bit. But one of them is called entropy. Another term related to entropy is control as inference. So what does this mean? Well, a soft actor is not deterministic. Whereas a deterministic neural network, you give it the same input 1,000 times, it'll give you the same thing 1,000 times. A soft actor, it's randomized. It generates multidimensional Gaussian distributions from which actions are sampled. So when the duck chooses a velocity, it's actually having a bell curve set up, a mean and a standard deviation for speed, and another bell curve, a mean and standard deviation, representing how much it turns to the left or to the right. And what its actual speed is and what its actual yaw change is are sampled at random. And now we're going to change the value that we talked about, the Bellman's equation. We're changing it such that in addition to the reward and in addition to expected future values, we are adding entropy. So we're subtracting alpha, which is how much we care about entropy. It's a hyperparameter. And we're multiplying it by this value. What the heck is this? This is entropy, and it is the negative log probability of having selected that action based on this observation. So if the duck knows exactly what it should do in order to get a good reward, it can make very narrow probability distributions because it knows exactly what it should do, and the action will be sampled from just there. But if the duck has no idea what to do in order to get a reward, it can make very broad probability distributions, which means it will move in very random ways. And by doing that, it will reward itself and be more likely to find extrinsic rewards. Are there any questions about this? Because I think a lot of stuff in this presentation just blew my mind the first time I heard of it. But if there aren't any questions, let's see how ducks do when they have entropy. Well, if we just go 100 epochs at a time, after 100 epochs, these ducks, I think they are so much more exploratory. They're going everywhere, and that's the good way to do it. Not only have they found this lesser exit, but a lot of them are just sort of randomly thrashing around in this area. So if we compare how well these ducks did, N is the ducks that didn't have entropy, and these are the ducks with entropy, E. And you'll notice they were pretty good. They found the good exit about 40% of the time. And this dotted line is going to be dividing these ducks, which had no intrinsic rewards, from ducks which actually did have intrinsic rewards. So these are doing much better. Here, let me go to the end of that training session. So a lot of these ducks are going to the better exit. But can we do even better than this? I don't have these plots in this presentation, but if you go to the paper, I should be able to send a link eventually. There are plots with which you can see which exit they were choosing based on how many epochs had passed. So after this much training, what were the ducks usually doing? After this much training, what were the ducks usually doing? And you'll notice it really seems like the ducks choose to take the first exit they find. If they find the exit on the left, they'll go to the exit on the left. If they find the exit on the right, they'll go to the exit on the right. So entropy makes it a lot more likely that they can find the exit to the right. But it's still, the ducks who find an exit, they usually just take that exit. How can we fix that? Curiosity. We're going to start with a prediction error curiosity. It's easy to work with. But there's another intrinsic reward, curiosity, which is also called active inference. So control as inference was about randomness in control, randomness choosing actions. Active inference means that the duck is actually going to be choosing actions which it thinks will provide more information. That is curiosity. Prediction error curiosity. It's not that easy to understand, but I think it works. In addition to an actor and a critic, let's give these ducks a forward model. There are a lot of names for a forward model. They're also known as world models, transitioners, generators. I think there are a lot of names. But what does this look like? A forward model is a neural network, as per usual, which is given an observation and an action, and it predicts the next observation. And this is going to sound a little strange, but the adjusted value, we're still using rewards. We're still using expected future rewards. We can still use entropy if we'd like to. But this term right here is eta times p, where p is a curiosity value, which is, in this case, the prediction error, the forward model's error. We are increasing Q value when the forward model makes mistakes. This blew my mind when I first sort of figured out why we're doing this. The way I like to say it, this forward model, it's called a world model for a reason. It represents the duck's understanding of its environment. You know, if it's in this position and it does this action, that's what it's going to see next. It's the understanding of the world. But the actor gets to just sort of walk in and say, you missed a spot. You missed a spot. You want to understand the world where you missed this. And so the actor can take the forward model in places it doesn't understand yet. And that's curiosity. And it works. Check this out. So this is ducks which are using prediction error curiosity. And this is ducks which also have entropy. It's generally better to have both of them, active inference and control as inference. And you also notice that before any training, all of the ducks are doing exactly the same thing. And that's because all of these ducks are using the same random seeds. And that can make it really clear that if the ducks are doing better than other ducks, it's not because of randomness. It's because those ducks are genuinely good ducks. So this one's really interesting. If we just go forward 100 epochs. So the ducks have done 100 episodes. They're exploring around. They like what they're seeing. They find the left exit first. Of course they do. The left exit is right there. And they like it. There's a reward right there. But after another 100 epochs, you'll notice the ducks aren't taking the left exit anymore. They're bored. They got bored of the left exit. The duck went to the left exit so many times that the forward model got really, really good at predicting what it would see. The accuracy went up, which meant curiosity in that direction went down. And now the actor, it's not getting the value it used to. So the actor can say, well, I can get a better reward if I move in places that we haven't looked yet. So it goes to the other path. I'm a little disappointed with these results, actually. It seems like a lot of these ducks are just sort of spinning around in the very beginning. And I can understand that, because if it just spins around in slight different ways, it can see the world from completely different perspectives. But regardless of that, ducks with prediction error curiosity, we compare that to ducks without entropy and without curiosity, they're doing better. And they do even better if you also have entropy. But overall, we can tell these ducks, they're getting bored taking the same exit over and over. So they try the other path and they find the better exit. And this works best when you're using both of these at the same time, control as inference and active inference.
Yeah, I don't know if I'm thinking about this wrong, but on the right model,
Yeah.
in a bunch more epochs, would they grow bored of the right exit too?
I think in theory, yeah. I might need to consult some of the other plots that I've made for the paper, but I think in theory, if we allowed them a lot more time, they would understand what was going on here.
Okay, so there's no like value that keeps them wanting to go there despite the low curiosity?
Wouldn't, once the ducks consistently find a path to the most rewarding exit, wouldn't the kind of extrinsic reward part of the critique function kind of dominate over the curiosity and entropy aspect of that, causing it to converge, or is that really not a guarantee?
I think you're absolutely right about that. It just sort of happens in this particular circumstance that I made the extrinsic rewards so high that when the duck does eventually find them, it's less concerned about curiosity and it's less concerned about entropy. Although I will say they're still interested in entropy and they are still interested in curiosity, which means you can actually have the ducks, they're not only finding the correct exit, they are finding the perfect path to the correct exit. By using curiosity and using entropy, they can find the best way to get to the good exit.
Got it. Thank you.
Cool. But, what if? Remember those question mark blocks? What if the question mark blocks are randomly changing color? We call that curiosity traps. And I'm sure that if I ask you guys, you can probably guess a reason why.
Well, they would constantly be fooling the prediction, so the duck would be incentivized to just stay in that area instead of actually finding an exit.
That is exactly the problem. Thank you so much for saying that. If you've ever had a seizure, or if you know you have epilepsy, close your eyes and I'll tell you when it's okay to look. So look at this. So this duck, it's doing its best, but those blocks are completely changing color absolutely randomly. So if you've ever had a seizure, I think it should be good to look now. The blocks are changing much slower. But every single step, the blocks change color, which means, just as you were predicting, the forward model won't be able to perfectly predict what they look like. The forward model predicts just the color in the middle of all those colors. So that's the least wrong it can be. So how does this affect these ducks? I'm just going to skip to the end of training here. But you can see, it's a little difficult to visualize, but more ducks. On the left here, we have the two ducks we just saw, prediction error curiosity and also with entropy. But on the right side, we have the same ducks when they have these curiosity traps. And so many more of those ducks are incentivized. They're really satisfied by just rolling around here because they're getting more rewards. So if we have another plot comparing these, this is the impact of traps on the likelihood of ducks choosing the correct exit in the last 10 episodes. So P, prediction error curiosity, they were doing it about, it looks like 30% of the time maybe. But then we have traps as well. they're doing just about as well as the ducks that didn't have any kind of intrinsic rewards at all. And entropy and prediction error curiosity is affected even more. The ducks, the forward model, it can't predict the question mark blocks, so the ducks are mesmerized. How can we fix this? The free energy principle. Finally, we're going to talk about the free energy principle. We mentioned it very earlier in the beginning. Biological agents like us, we want to minimize free energy. And free energy, F, looks like this. Accuracy is something we've already looked at. Accuracy is how well the forward model is predicting the next observation. Complexity is more difficult to understand. Complexity compares a prior inner state, P, and a posterior inner state, Q. These are two probability distributions, a prior and a posterior probability distribution, and we are comparing them using Kolbeck-Leibler divergence. KL divergence is how you can compare different probability distributions. So in other words, we want to make accurate predictions. We want our forward model to be accurate, but we also want the forward model, our worldview, to be comprehensive and reliable. So accuracy, I think, is relatively easy to understand, but complexity means how much our worldview changes just based on getting some new information. If we get new information and our worldview completely changes, the prior is completely different than the posterior, that would be high complexity, because what we thought of the world, it exploded and we have to replace it. However, if we have a really good understanding of the world, then when we get new information, we'll say, yeah, that's new information, but it's nothing surprising. And that means the prior and the posterior are very similar, very close together. And it just so happens that complexity is a better curiosity value than inaccuracy. So complexity, comparing our worldview before, prior, and after, posterior, seeing a new observation, that is a very good curiosity value. But how do we get it? Getting accuracy, that was pretty easy. All we needed to do was predict the future and see how wrong we were. You know, that was prediction error curiosity. That was easy to do. Complexity can be a little more difficult to find. So this is a forward model as a variational recurrent neural network. This is why we had to talk about recurrent neural networks earlier. Buckle your seatbelts. This is intimidating. So here's a forward model, and we're going to initiate it. Before any steps within an episode, we're going to have a hidden state. A hidden state, which, I mean, nothing has happened yet. So we're just going to have the hidden state be a tensor, a collection of numbers, but all of those numbers are just zero. We haven't experienced anything in this episode yet. We are also going to initiate a previous action. There is no previous action yet. That's just zeros as well. Now, using the hidden state and the action, we are going to make a prior inner state, P, here. So we're going to use the hidden state and the action, and we're going to make a mean and a standard deviation, which represents our worldview at the time. This prior inner state is our worldview. And then we are also going to have an observation, O, here. And so we're going to make a posterior inner state, Q, using not only the hidden state and not only the previous action, but also an observation. And we're going to use that information to make a probability distribution, the posterior probability distribution here, which gets just this much more information. And so comparing these with Kolbeck-Leibler divergence, we can see how much that observation has completely changed our worldview at the time. So moving on a little bit, we're going to sample Z. You can see here we're sampling from this probability distribution Z. We're calling this ZQ because we're getting it from the posterior interstate here. We could actually just get Z from the prior interstate as well. Don't worry about it. I'm going to use that later in this presentation, but it's just kind of a cool thing you can do. It's more important to use this posterior, because using this posterior Z value and this hidden state, we're going to make a new hidden state. So this new hidden state represents all of the information that the duck has gathered up to this point, including this new observation. And so using this hidden state and using the next action, we're finally going to make a prediction about the next observation. So this is the accuracy value, and so on. So you can see these little dotted lines. We're just going to use this hidden state and this action to make another prior interstate and another posterior interstate using the next observation here. And so using this, you can see we have an accuracy value and a complexity value. So minimizing free energy means you make accurate predictions, maximizing accuracy, while also having the posterior and prior interstates. You want them to be very close together so that complexity is as low as it can possibly be. So that's really something. So just to bring it back to the value that we're trying to calculate, the value now includes all of the aspects of free energy, expected free energy. Those parts in expected free energy include extrinsic rewards and entropy, and the complexity value. I call it hidden state curiosity. This is curiosity based on interstates. There's another intrinsic value here. It's called imitation. We're not using imitation. Imitation would mean we would actually give the ducks correct answers. We would give the ducks the best possible actions. And then the duck would be rewarded if it made actions which were very similar to those actions. So the duck is trying to predict what the best actions would be. And that's just cheating. That's just cheating. If we're working in the field, if we're working with actual robots, imitation would be fantastic. You can tell the robot exactly what you want it to do, and that'll really speed along the robot actually learning to do it. The other parts will help it, but imitation, I think, would be the most important one. Here, with these ducks, I don't care about imitation. That would be cheating. That would make them supervised ducks. I want them to be self-supervised ducks. Are there any questions about this page? Because I think this is a big one.
Yeah, I was hoping you could contrast hidden state curiosity with like regularization, because this kind of seems the kind of complexity of the interview kind of, and minimizing that kind of reminds me of regularization, and I just want to know if that's a completely different idea or if they're actually pretty similar.
Not only is the prior sort of trying to predict the posterior, the posterior is also not supposed to be too different from the prior. So it is sort of like the two sides here are trying to meet each other in the middle. And it just so happens that meeting each other in the middle while also trying to make accurate predictions leads to a comprehensive and consistent worldview in the interstates. I hope that helps. So if we can look at how these ducks are doing, here are hidden state curiosity ducks, the same with entropy. And on the right side, the same things with curiosity traps. And I'm just going to move to the end here for time. But so after 5 minutes of training, just like all those other ducks, not only are all of these ducks, a lot of these ducks are choosing the exit on the right side, but also very few of them seem like they're just spinning around. So if we check out this plot that we've seen before, hidden state curiosity, these ducks are about 60% likely to choose the better exit in the last 10 steps. And with entropy, it's about 80% of the time. And that's so much better than all the other ducks. But more importantly, even when you include curiosity traps, the ducks with prediction error curiosity, they're mesmerized. But the ducks with hidden state curiosity, instead of looking at accuracy, they're looking at complexity. They don't care about the randomly changing color blocks. So these ducks are great, even with curiosity traps. The random colors bore them. So even though they're not accurate, the accuracy, it can be pretty low sometimes. But that doesn't matter, because the complexity is still very low. The prior might say, I think that's going to be a random color. And the observation shows a random color. And the posterior says, yes, it was a random color. There's no new information here. Instead of looking for things it can't quite predict, it's looking for things which provide new information. And that's the way to do it. I think this is cool. It blew my mind. So let's try seeing the maze from a duck's point of view. And I don't just mean what it's seeing, I also mean what it's thinking about. So if we start here, we're looking from the perspective of a duck with entropy and hidden state curiosity. Those are the best ducks. And on the left side here, this is the observation that the duck is getting. So right now, this is the very beginning of the maze. It has 0 steps so far. There's no action yet. The speed is 0. And we've seen this before. It's seeing a block on its left, some blocks a little farther away, and some blocks a little farther than that. And if I just go one slide forward here, there we go. So this is after 1 step. It looks like it turned a little bit to the right. It looks like it's moving very quickly. And so it's moving along. But let's also check its predictions. So in the center here, we have the prior prediction. Remember, we could sample the z value from the prior or the posterior, and we use the posterior, but we can also use the prior. So this is the prediction based on a z value sampled from the prior. And on the far right side, the same thing with posterior. So these predictions are pretty good. They're pretty blurry, but you can see it's saying, oh, it's going to be olive colored here, it's going to be pinkish here, it's going to be grayish over there. And not only that, not only are these pretty accurate, they're almost identical, which means the prior and the posterior are basically the same. So complexity very low, accuracy pretty high, very low free energy. So if we just let this keep going, we can watch the maze from the duck's perspective. Here we go. He goes forward, he goes right, he goes left, he goes right, he goes forward, he turns to the right, and he chooses the good exit. Yeah! So if we go back just a little bit, you can see he's predicting for some reason there's going to be red over here. And I can see why I made that mistake, because if we go back to one of these observations, yeah, you can see there was a red block right there. So it thought it was going to see that red block. And it doesn't, but it's still relatively accurate. And you can actually see a little bit of difference between the prior and the posterior. When the prior made its prediction, it looked like this. When the posterior got information, new information from a new observation, it thought, well, it looks like we're going to be slightly farther ahead. But that's a duck. We can see from the perspective of the robot, from the robot duck, and that's so cool to me. I'm so glad I get to work on this.
I'm sorry. Could you please explain one more time why the DKL complexity measure is not affected by curiosity traps?
Yeah. The prediction error curiosity did not it did not use complexity at all. It only used accuracy, which means it was comparing its prediction to what it actually observed. So when it sees something which is randomly changing color, it'll never be able to perfectly predict that, meaning that there will always be an error. And having always an error means that there will always be curiosity value in that direction. The ducks which are using hidden state curiosity, using complexity, they're still trying to make accurate predictions, but it'll still have the same problems as the other ducks. When it makes a prediction of a randomly changing color block, it's still going to guess gray because that's the closest it can always get. But instead of being engaged with that, instead of being interested in inaccuracies, it's interested in observations which completely change its worldview. Meaning that in the beginning, when the ducks are just starting to train, they might be really interested in the randomly changing color blocks. The ducks which are using hidden state curiosity, the complexity might be pretty different seeing blocks before and after they change color. But eventually the agent realizes that what the block turned into doesn't give it any new information which it can use to make more accurate predictions. But complexity can be minimized by not being surprised by random colors. The prior understands that there's uncertainty with the color, and the posterior sees the color and says, yes, that I was uncertain about that, but there is no new information here. So if the duck was expecting it to be a random color, and it is in fact a random color, the worldview did not change before and after.
So it's seeking out observations that change its worldview. Is that correct?
Yes.
Got it.
It's as if the actor and the forward model are antagonistic. They're competing. They're adversarial. The forward model wants to minimize free energy, but the actor wants to maximize expected free energy. The actor is trying to find things in this world that it does not understand. And the more it sees those things, the more the forward model does actually understand it.
I think I understand better. Thank you.
Okay, thank you. I'm really glad to be sharing all of this. I want to share it with the world, you know. So there's one more example. I hope this one won't take too long, but we can spend as long as we want. Instead of having one maze, a biased T maze, what if we have a sequence of mazes? One maze which is expanding over time. So let's start with this really easy maze. You can see the duck starts here. There's just a left. If it goes to the left, it is punished with a negative reward. If it goes to the right, it is rewarded with a positive reward. But after 500 epochs of training here, well, the ducks are pretty good at going to the right. They figure that out. But after 500 epochs, we're moving them somewhere else. We're moving them to a double T maze. And now the only good exit is over here. Instead of just going to the right, they have to make a left and then a right. And after 2,000 epochs here, we're moving them again. We're moving them to a triple T maze. And now the only good exit is over here. You have to make a right and then a left and then another left. And so a lot of these ducks just give up. A lot of these ducks cannot handle this. So let's see some results. We've seen this kind of plot before. This is choosing the correct exit, the one on the right. And you can see all of the ducks are doing pretty well. It's even simpler than the biased T maze we were working with before. Ducks which have no entropy and no curiosity, they're figuring it out about 60% of the time. Not bad. And more importantly, if we look at this plot here, prediction error curiosity is impacted by traps. And even if we include entropy, it is impacted by traps. But hidden state curiosity, they don't care about these traps. It still works like that. And now we're going to move these ducks. They've trained so hard to go to the right, and now we're moving them somewhere where they have to go to the left instead. Actually, if you find the GitHub repository, which I link in the paper, you can see the videos. Like I showed you the videos for the biased T-maze. I made the same videos for these expanding T-mazes. And you can see the ducks with nothing, they give up. They just spin around. Well, they were already taught never to go to the left, always go to the right. And they never come to the conclusion, well, maybe I should try. Maybe I should try again. Instead, all of these ducks, when they stop getting extrinsic rewards by going to the right, they decide, well, I can still reward myself by going in random directions or going in directions where I'm not sure what to expect. And that helps them find the better exit again. And if we do this again with the traps, you'll notice actually prediction error curiosity impacted by traps. Hidden state curiosity not impacted by traps at all. But you'll notice this one actually did slightly better with traps. And I'm not totally satisfied with that, but if we actually go back to the previous slide, on this, in the T-maze, the agents were trained to go to the right. But agents with prediction error curiosity, if they had these traps on, they might have been trained to go to the left instead. Which means when they are brought to this double T-maze, they actually have an advantage. They were already taught to go to the left, and now the correct exit is on the left. So I think that's the reason these ducks, which were using prediction error curiosity, they actually did better with the curiosity traps. But that might just be me making excuses. I think what's more important is that when we move them to the triple T-maze, we see this again. The ducks with no entropy and no curiosity, they've given up. The ducks with entropy have given up. But the ducks which have hidden state curiosity, or better yet, hidden state curiosity and entropy, these ducks are doing very well, about 80% of the time. And that's pretty impressive considering how gigantic that maze looks. And more importantly, prediction error curiosity impacted by traps. Hidden state curiosity, they can ignore those traps. So the free energy principles, intrinsic rewards, they definitely help, but they don't care about curiosity traps. So in conclusion, minimizing free energy can help artificial agents like robotic ducks think in the style of biological agents like us. And that is awesome. Maybe someday we can fulfill Alan Turing's dreams of robots learning like human children can learn. And I hope so. So thank you so much for listening. This was a joy to present. I'll try joining the Zoom chat again.
Okay, so I think that Ryan, you want to ask a question?
No, I didn't have a question, but I did just want to say thank you for the presentation. It was really interesting.
Yeah, it was.
Thank you so much. I am slowly becoming someone who at least vaguely knows what they are doing.
No, it is really interesting, and you are a very good communicator. So,
I think the visualizations of the model's perceptions of the maze, I think that was a really nice touch that really helped communicate your point. And I thank you for taking the work to do that.
Oh, thank you.
Please let me know if this is maybe straying too far into philosophy and far away from kind of data science.
I think philosophy is exactly why I want to do this.
Okay, well, great. So I guess my question was, why do we use free energy as this proxy for this effect about, you know, uh, observational impact as opposed to, say, directly measuring observational impact? So let's say you have some weights between prediction state 1 or prediction state 2, and just you take the absolute value of their difference, and that kind of sort of also measures the, you know, the impact of an observation. And I guess I was wondering why we use entropy as opposed to something a little bit more direct, like, you know, comparing the weights of the model.
That's a really good question. And actually, I want to make a reference to a paper which I could not have written my paper without. I'm not stealing from this paper, but emotionally speaking, it feels like I'm stealing from this paper because I could not have written my paper without it. And they do something very similar to what you are explaining right there, where they basically do exactly what I'm talking about with free energy. But the way they get those values is by comparing their neural networks before and after. Specifically, we could just use a deterministic neural network to do that. But I think we would have the same problem with prediction error curiosity, because what's really important with the free energy principle is uncertainty, which means it's important to consider probability distributions of I'm very sure about this thing. I am not very sure about this thing. The answer could be anywhere. So the way that they do it is not the way that I do it. They use a Bayesian neural network, which means that every single parameter of that neural network is actually two parameters. It's the mean and standard deviation. And then every time you use the neural network, you sample new parameters. And so by using Kolbeck-Leibler divergence to compare the model itself before and after, you get that curiosity value. But I don't like that because when you have a whole batch of information and you train the forward model using that entire batch of information, you can only compare the forward model before and after the entire batch of information, which means you only get one value for the entire batch. So I think in the paper, they get around that by only using one observation at a time to train the forward model. But I don't think that's very efficient. I think it's generally more efficient to have huge batches of information to train all at once with. So I think the big difference between mine and theirs is that instead of using the entire model so that you can only get one curiosity value at a time, I'm using just like a variational portion of the model so I can get as many values as I want.
Yeah, I think that very clearly answers my question. Thank you.
Yeah, I believe that paper is called something like curiosity as defined by the free energy principle. The big change I made was having a model architecture which is based on something that we've worked on in my lab back at OIST. So I stole something from this paper and I stole something from the lab and I put them together, and sometimes that's the way it works. I think it's really great to meet all of you. I hope the school year is going well for you.
Thank you so much. Okay.
It was really nice to meet you.
Thank you.
I'll see you all eventually. Bye-bye.
Bye.
By the way, I've got a Patreon at patreon.com/thinkster. I want to thank all these squidlings and elder squids. Thanks.